And also, so you know, we have many, many speakers. All of them are exceptional. All of them are famous. And we have so many of them that I actually don't really spend a lot of time introducing speakers at the course, because we'll let Martin go ahead and introduce himself. But Martin is a long-term colleague for this course, one of the course organizers, and brilliant and fun.
Hi, thank you very much. It's my pleasure to welcome you to the 10th edition of the summer program at NITP. My name is Martin Monti. I'm a professor here in the psychology department and sometimes in neurosurgery. And I was one of you a few years ago, and then I got recruited here as a professor, and it's been great ever since. And it's been great after having had the experience of being on your side to have organized this for, I guess, or to have been part of this organization for about the last 5 years. And it's a lot of fun every year. You guys are different every year, which makes us different every year and exciting every single time. So, okay, 2 truths and a lie. I didn't have too much time to think this one through, but here it goes. I was the frontman of a rock band for more than 10 years. I had artwork on exhibit at the museum, and my 7-week-old slept all night yesterday night. So go easy on me. And the night before, and the night before, and the night before. So what I'd like to do for the next sort of 50 minutes to an hour is to go over what should be a particularly simple aspect of what we do, but is in fact extremely complicated. And I think has gotten more complicated in the last 5-8 years with really this massive emergence of data of task-free type experimental designs or analysis. So I want to sort of go over what I think are some of the biggest issues within preprocessing. Let me just get a couple get you situated. Also, this slide is pretty much going to summarize the time that I will spend talking for today and tomorrow. We're going to start, obviously, imagining that you've acquired some data, perhaps some structural data, and definitely some functional data, which I'm showing here with these sort of crummy, sort of pixely brains. And then, of course, after that, you're going to do all sorts of filtering to your data. And that's what I want to talk about today. And then we're going to move on, and we're going to go from there to how to analyze that actual data, perhaps how to turn it into some kind of common space so that you can relate your own findings to previous findings and sort of explain to someone else who's not in your lab where exactly your findings happen to be in the brain, and then perhaps some method of bringing together analysis, single subject analysis, sort of from a number of individuals. If all of this has gone well, of course, sort of you end up publishing it in Science. If this goes less well, sometimes you publish in a journal in support of the null hypothesis. Underappreciated journal for sure. I do have to make one point very clear. You might not be this kind of person. You might be this kind of person. You might like better task-free analysis, which today are so sort of ubiquitous. Needless to say, sort of particularly the preprocessing component is just as important. In fact, if you ask me, it's even more important. So what I want to sort of cover today is exactly sort of this aspect of the analysis. And sort of between today and tomorrow, we're going to go sort of over the other boxes in here. So all the fun stuff, that's what I do. Let me allow me one slide to set my language straight. And I do it more for me than for you, because I have horrible habits when I talk about these things, and I get my language all mixed together. So I will try to abide by the following convention. That when you acquired a single, when you do a full sampling of the brain once in a functional sequence, I'll refer to that as a volume, which is the proper term. A typical run is made up of a bunch, right? A series of volumes acquired at a certain repetition. And I will try very hard to refer to this as a run. Unfortunately, I will often say scan to refer to either of these two things. If I do that and I'm unclear, stop me, ask me, I'll tell you which of the two I meant. The second intuition I want to leave you with is that throughout today and tomorrow's lectures, it makes sense to think about a run in two different ways. And different parts of what I'm going to talk about fit better one of these two intuitions. One is that a run is a bunch of sort of heads, right, acquired one after the other. And sometimes it makes good sense to think about it this way. The other way that it makes good sense to think about it is to have one head and a time series associated with each voxel within that head. And again, one of these two might be more intuitive to you, but throughout what we're going to talk about today and tomorrow, I really want you to have both intuitions in mind, because one of the two will make more sense at each of the steps we discuss. So let's dive into preprocessing. So what is preprocessing? Well, in its sort of broadest term, it's a series of data transformations, filtering, data conditioning, aimed typically at reducing sources of noise. Right? And there are some reasons why we do this, and I'll get into them in a moment. Now, with respect to task-based analysis, so your standard, task control condition type analysis, the filters that you apply and the order in which you apply them are somewhat standardized. I don't think it makes it any more trivial. I don't think it shouldn't mean that you shouldn't question the order in which you're doing things, but nobody's going to get upset at you for following the vanilla type series of preprocessing steps. Now, maybe you don't want to do that, and you might have very good reasons. There might be good data to not to do things the way we currently do, but I do get a feeling that most people are peaceful about the typical order these things happen in a task-based environment. In a task-free environment, which steps to apply and in what order is a huge can of worms. The order is a big problem, and which steps to apply depend on which kind of analysis you're doing. Right? So sometimes bandpass filtering, for example, you might want it, you might not want it. Smoothing, you might want it, you might not want it, according to what kind of analysis you're doing, how you end up segmenting the brain, et cetera, et cetera. So particularly if you're doing a task-free analysis, you have to be able to think very deeply about these steps. You have to know exactly how each of these steps is affecting your data, because it will, and there's plenty evidence to show this, it will change your results if you do, for example, graph theoretic analysis. If you're one of those people, these decisions that might seem innocent will change in a disconcerting way your results. And if you've done some of those analyses, I sure have, and you have tried it with different preprocessing streams, you will have noticed that it does make a big difference. All right? And this, we're still trying to iron this part out. So that's why I think it's just all the more important that you have a deep understanding of what's happening. So where does noise come from, if that's what we're trying to diminish? Well, all sorts of sources. Really, the two main, you can think of this, you can think of noise a bit as a penalty for what you want to do. For everything you want to do, you pay a penalty, and that comes in the form of noise. For example, you want to be alive in a world that exists, and then you get thermal noise, and that's just it, right? If you don't have thermal noise, then noise in your analysis is the least of your problem, because the world doesn't exist anymore or something like that. So that you just, you can't do anything. You're alive, and the world exists. Thermal noise. System noise, on the other hand, might be the penalty that you use for using a certain technology. And this might come in all sorts of forms, including a faulty wire that creates spikes in your images and anything. It can be all sorts of things. But this is tied to the type of hardware you're using. You then want to use the hardware in a specific way that allows you to acquire rapidly over only 2 seconds. It allows you to sample a whole human brain at some resolution. Well, you're going to pay a penalty for that. And that comes in the form of slice acquisition timing, right? And its associated issues, which we're going to get into. Even worse idea, you might want to put a human inside an fMRI. Gosh, all sorts of penalties to pay for that. You get oscillatory physiological noises, right? These tend to be at a very different frequencies than those we are interested in, but they get aliased into low frequencies and sort of, I'll get back to this, and tend to be very problematic in your, and tend to be very visible often in the signal. Even worse, you put a head inside a nice and really homogeneous magnetic field, you're going to do all sorts of bad things to that magnetic field. The sinuses, the ear canals, screw completely around with the niceness of the magnetic field that the nice people at GE, Philips, and Siemens provide for us. So we go in and spoil it by putting humans in there. Probably one of the worst ones, you put a human in there, short of nailing their ears with non-magnetic nails, obviously, to the bed, they will move. And I suspect even if you nail their ears, which you shouldn't do, but even if you did, there would be all sorts of movement related to heartbeat and sort of tugging, for example, of the blood vessels that climb up the brainstem, et cetera, and that would still create motion within what you're observing. And needless to say, there are all sorts of psychological variables that might be very important and might creep into your signal, particularly maybe in the form of slow frequencies. Alertness is bound to change over an experiment, learning effects, all sorts of things like that. Right. So these are sort of a broad brushed panorama of the kind of sources of noise. Of course, there's white noise, but we all like white noise because it's easy to cope with. Just do a bunch of trials. Now, what can you do about it? Well, there are two ways of going about this. One way is before scanning. And just before scanning, you just want to try to maximize what you got. Right? The simplest advice would be choose great technology, but this might not always be within your, you can't always sort of put your hand in your pocket and say, oh, I'd love to have a, 7 Tesla machine. So not all of us can do that. So you might be stuck with whatever technology you have at your institution. However, you can do plenty, even just by choosing, for example, good sequence parameters. You might want to choose very carefully what is the echo time that you're interested in according to what part of the brain you're interested. If you choose it poorly, you might end up with a big black blob exactly in the part of your brain that you meant to study. So that's one example. You want to be very well informed on how healthy your scanner is. I happen to have been at an institution where for a little while there was a faulty cable, but nobody was checking their own data. And we used to acquire data in batches. And then it turned out for 2 weeks, everybody had spikes in their data, which rendered it useless. But because nobody bothered to look at sort of these things, we all acquired a couple weeks worth. Actually, they all acquired. I wasn't, just by coincidence, I wasn't scanning at the time. They all acquired a bunch of useless data. I would have probably had the same problem. I just wasn't at that time scanning. So this is stuff that happens before, right? But what I want to talk about today is what happens after you've acquired the data. What can you do about these sources of noise? And really, the simplest thing to do, which you should always do, is look at your data, right? Rule 1 and rule 2 are look at your data. But after that, you can do a series of preprocessing, which is what I'll focus on. I'm going to keep to what I consider the standard preprocessing, so a number of steps. You will hear throughout throughout these 2 weeks of alternative ways of doing it. ICA is probably one of the most employed alternatives, where you actually use these data-driven methods to find signals, and then you deem them, or you train a classifier to label them as noise or non-noise. And you'll get more of this later, so I won't focus on it. So let me really focus on this part here, right? So sort of the principle of detect and correct after the fact. So why do we do this? Well, 2 reasons. One is we really want to increase the sensitivity of our analysis, right? And the second one is that we want to ensure the validity of the model for what we're going to do after, which is the step after the analysis. And I've put ensuring in quotes because whether we truly ensure that we are meeting the assumptions of the model doesn't quite seem to be the case, but that's why we do this. Let me give you just a quick example on the SNR. Just imagine you have the simplest experiment you could ever do. Sort of an on-off block design, maybe 8 TRs on, 8 TRs off of some kind of task, maybe looking at faces and versus rest or versus scrambled images, something like that. You take one voxel and you look at its time course, and you can look at this time course and you might be able to tell just by eye that there's a certain signal and there's a certain noise, right? What is the signal that we're interested in? Well, obviously, the signal to us is the change, right, in the average off from the average on, right? That deflection in the data I can explain because it's what I inserted in there. It's my manipulation. So what is noise then in this graph? If that's a signal, what is the noise? Everything else, very good. Any other oscillation that is in there that is not the deflection from whatever is my average baseline to my average on, from my average off to my average on, that is all junk, is noise. I don't know why it happens. You know, why does the line squiggle during the on periods? I got no clue. I mean, maybe I've inserted by mistake, you know, something in there that makes it squiggle, but given this very simple design, I have no clue why it squiggles. Why does it squiggle during the baseline? I have no idea, right? So that's my signal to noise ratio in a visual sense. Right? You can look at this other time course, and again, there's a clear signal, right? The difference between sort of the on and off periods, those green lines. We still have those high frequency squiggles that I can't explain, right? But as you can see, there also is a huge low frequency big squiggle, right? So now it's pretty obvious that as compared to before, our signal to noise ratio is very different. And notice that this is actually the exact same time course as the previous slide. I just injected artificially in there that big low frequency fluctuation, right? So really, our preprocessing is to go from something like this to something like this, right? This is what preprocessing is about. It's taking things that just appear to be as noise and trying to clean them off, perhaps by explaining them or by saying, well, this is really not relevant to my task, so I'll just do without, right? For example, this big slow frequency is really irrelevant to my task. It might be meaningful. Maybe there is a change in alertness in my subject. You know, they really get interested, then they fall asleep. Maybe my task is too long. Maybe that's what this is saying. But it's irrelevant with respect to my on-off, right? The only thing that I'm trying to explain. So we're trying to do this, right? To go from here to here. The second thing is that we're gonna then take this time series, apply a certain statistical model to it, the general linear model. I'm sure you're all pretty familiar with this. And this model just has certain assumptions about one of its terms. And we're gonna sort of go into some detail into these assumptions tomorrow. So get some coffee. But this is the second reason why, at least nominally, this is the reason why we do this. It turns out it's more complicated, but it doesn't matter. So these are the two reasons. Now, let me go through what I think are sort of some of the most salient preprocessing steps. Since someone made this point a couple years ago, these are not the only steps you might want to do. There are some additional steps. Dropping a couple TRs at the beginning is a very typical thing to do. But I want to focus on those that I think are sort of the most interesting ones. And in your slide set, you will see at the very end, there are a couple additional steps. One is brain extraction. Can I ask how many people work with populations that are not your average undergrad, so that the brain is not the perfect undergrad brain? Oh gosh, nobody scans undergrads anymore? Okay, then maybe I'll speak slightly faster to try to get to the brain extraction. We've created a software that allows gives you a slightly easier time when you have non-brains that are not the perfect undergrad, the perfect 22-year-old undergrad. And it's free, you can download it. If you use FSL, it's literally just one line. You can download it for free. Anyway, we can talk about this later. All right, so off we go. Very first one, slice time correction, right? And the idea behind slice time, as you probably know, is that in order to acquire to sample the brain in full over sort of at a rapid speed, well, to sample the brain, we don't sample it in 3D, we sample it in 2D, right? We sample the brain in every volume as a number of slices, right? So we acquire one slice after the other. And of course, it takes time to do this, right? In your vanilla epi sequence, it might take 2 seconds or 3 seconds or something like that. So this means that each slice that you're acquiring is at a different time with respect to the neural events that you're trying to capture, right, with the slice. So it might go something like this, right? Let's just assume that we had interleaved slices. I'll capture the first one, then the third, 5, right, and go on. And it'll take me exactly half the TR to capture the first half, right, of the slices. And this will take exactly 1 second, assuming a 2 seconds TR. And then once I'm done with these, I will capture all the remaining ones, all the even ones or all the odd ones, depending on how many slices you had or how you did it. Now, again, the problem is that I am trying to capture, I capture over 2 seconds the full brain, but the neural events then that sort of the occurrence of the neural events with respect to my slices is now uneven. Right? And this is very problematic. Here's why. Imagine you had take a brain and let's focus on a small piece of real estate inside this brain, which is blown up here. And this little piece of real estate, let's just assume that the neural events in there and the consequent hemodynamic response function generated from those neural events or associated with those neural events is exactly the same for any piece of for all this piece of real estate, right? The exact same thing is happening everywhere inside that sort of orange area. And notice that that orange area spans 3 slices, slice 15, slice 16, 17. Again, let's assume we're doing an interleaved acquisition. So here's how this goes. The black line is the HRF associated with those neural events, right? But we're sampling this black line at different times for the slices, right? For example, the neural event starts and we acquire 15, 17, and then a second and a half later, we acquire 16. Right? And you've already seen that 16 is at a completely different part of the hemodynamic response function than 15 and 17. Right? And the same happens later, 15, 17, 16, 15. So as you rise, right, the slice that is captured later will always appear to have a stronger signal. Right? As it falls, you will capture 15, 17, 16, 15, 17, 16, 15, 17, 16. So as the HRF falls and you're sampling it as it falls, the slice that you're capturing last seems to fall faster. So if you now plot and interpolate your sampling of this smooth HRF, what you get is pictured in D. Right? The slice acquired latest always appears to have a stronger signal and then dies off faster than those acquired early, right? Which appear to have a comparatively lower signal but last longer. And this is a complete artifact. Right? This is junk, complete artifact. This is not what your data are, right? Complete artifact. So the idea of slice timing correction is to interpolate so that we pretend that these 3 dots were actually all acquired in the middle or all acquired at the same time. That's the idea behind slice timing correction. Right? Now, do people do this? Well, in task-based analysis, most people actually, it turns out, suggest not to do it. You can, but a lot of people say, well, look, it's not that helpful, first of all. It doesn't do that much to our data, and it does require interpolation. Why should you interpolate once more your data? You're already going to interpolate them so many times. Why should you interpolate the data one more time if it doesn't do that much? Although, of course, it might depend on your experimental design. If you have a block design, who cares about slice timing correction? But if you have a fast, random, jittered, event-related design, then it might be very important. It might worsen artifacts. By interpolating, you might smear spikes across your time course, which could be very problematic if it happened. And also, its interaction with motion correction is unclear. In fact, a lot of people think that these two, motion correction and slice timing, should happen at the same time, but just nobody has cracked that nut yet, or nobody has wanted to crack it, one of the two, probably the latter. On top of this, so on top of these negative factors, there are some positive factors. Look, first of all, we do spatial smoothing across slices. And this, if you're doing, for example, an interleaved acquisition, this really sort of moderates the problem, right? It mitigates it. Of course, if you're doing a sequential, then the bottom of the brain and the top of the brain the first and last slice will still be acquired far away in time. But sort of if you want perhaps the transition, you're smoothing out the transition across. So it might be more important if you're doing interleaved versus non-interleaved. Sorry, spatial smoothing may exert its effect and may diminish this effect more in an interleaved versus non-interleaved scenario. On top of that, if you're doing a task, then the suggestion is always to mismatch your task and your TR. Not only, perhaps you can always have your task either start at the beginning half the time and at the middle half the time, or maybe you can just let them roll independently, which is what people suggest. As long as your task happens sort of at all points, begins at all points throughout each TR, then you are sampling, right? Your task is starting and getting sampled in all the possible ways, so to speak. So this typically is what most people do when they have jitter event-related designs, fast event-related designs. And then on top of that, you typically, in task designs, you typically do use the temporal derivative at least, and that tends to soak up some of these effects. There is some cost to that, but sort of it ends up in there. So for all these reasons, people often say, look, you know, do it, don't do it. It's sort of not a big deal. However, if you're in the world of task-free, then everybody does it. Right? And most of these issues that I mentioned don't change, with the exception of the mismatching of TR and task. Right? I mean, it might be happening. Sorry, with the exception of the temporal derivative, which you can't use because you don't really know what is the task or what is the cognitive processes that are happening. So this is a clear division, right, between the two fields, between the two types of analysis. Sorry. Now, I should say, so Mark mentioned Angelo Mosso's balance, and you should know that Angelo Mosso, when he was describing this, was already concerned with motion. So motion, which is probably the biggest offender in the world of functional MRI in terms of artifacts, was already a problem in the original brain sort of brain flow measuring device. And it keeps being a huge problem today too. Here's one example. I borrowed this from the FSL people. So here's a subject that is having a party during the MRI. And you can tell, right? You can look. You see it right there. Now, what's the problem with motion? Well, there are two really, really big problems. The first is that the type of signal change that motion can induce, I mean, is orders of magnitude greater than anything the brain is ever going to do in the way that we see it through fMRI. Right? So sort of the delta that motion can impose is so much bigger that it will eventually dwarf your signal of interest. And I'll get to this in a second. And second, of course, you lose the correspondence. If somebody, of course, what you're acquiring is sort of a grid, right, of voxels. And if now suddenly my head has moved, the correspondence between a voxel and a anatomical part of my brain is completely gone. So imagine a subject doing only one tiny motion, somewhere in the middle, sort of they move down. God forbid the two areas you are interested in are actually one on top of the other. And so now the neurons that were in the original area have gone out of that voxel. The neurons that were in the top area have now moved in the voxel of the bottom area, and you don't get anything, right? And your experiment is exactly half the time one process and half the time the other process. On top of that, now you really don't know, you can't really point at a piece of the brain and say, oh, this was X part or this was Y part, right? Huge problem, because that is what you want to end up claiming in the end. And here's a beautiful example from Huttel and colleagues from their textbook. Just take any epi and let's focus on sort of this this section of it. In fact, inside in the blue square. Let's just say that the numbers you're seeing here are the raw values that come out of the MRI machine when you did this experiment. At some point throughout one run in one volume, and now the subject moves by one voxel. Right? There's a translation by one voxel. Everything has moved posteriorly by one voxel. I mean, one voxel, if the voxels are 3 by 3 by 3, this is a 3 millimeter movement. Okay? Now look at the numbers. One has gone from 500 to 663. That's a pretty big jump. But notice those, for example, this one here, which is this guy, went from 89 to 507. This amount of change, nothing in the brain is ever going to do this other than an artifact, right? If you hammer visual cortex with blinking light and sort of to the point that you're making somebody almost sees, you will get a few percent signal change. Right? You're never going to get something this big. So now go back to the signal to noise ratio, right? The noise is just orders of magnitude bigger than your signal, which means your noise is going to dwarf entirely what you're interested in. Right? i.e., you can't see it, t-test, non-significant, no publication, gone. Right? Bad, we don't like that. So what we do is we do motion correction. And there's one tiny thing I really want to point out because it makes a very important experimental point. here's what you would typically see, right? So you do an analysis without motion correction, and there isn't much happening. Then you go, oh my gosh, I forgot, yeah, the motion correction, click. Right? And now you do it, or you redo the exact same analysis, and here it is, right? So what happened, obviously? Come on, what happened? Clearly. There you go. You removed the noise, right? You modeled, you fixed it somehow, and you've improved your signal to noise, and now you get your nice result. Bingo, fantastic, publication, science, 10, you're done. Now, however, this could happen too. You have a bunch of activations, right? And then you go, oh my gosh, or maybe it's your RA. You go like, come on, you didn't press that button. It's a very important button. Press it, redo it. And then he or she comes back to you a couple days later, ideally 5 minutes later, but sometime later, and they show you this. And now you go, oh my God, I lost all my activations. What happened? Excuse me? But I lost sensitivity. I'm sorry, yes? I got rid of the false positives. So what is the difference then between the top scenario and the bottom scenario? When must the motion have occurred? During my time of interest. If the motion happens during the task, there will be all this extra activation due to the motion that will look like it was in your task, but it wasn't. That's why you get all these extra activations. That's why it makes complete sense that when you clean off the motion, you get fewer activation. It's just you're getting the good ones. You got rid of the crummy ones. Right? So both scenarios are possible, but this makes a very important point. You want to make sure when you design your experiment that you try to decouple your cognitive event of interest from any kind of motion. It might be a good idea, for example, if you ask your subjects to respond, to have them do the cognitive task and then hold their response, their actual physical response, till, who knows, a few seconds later or something of that sort. Okay? Because if you get task correlated motion, then it's difficult to tell apart which part of the activations have to do with motion and which do not. And even if you use motion correction, you might still, right, remain with motion-induced activations in there, right, and be unable to tease them out. Very important. How does motion correction work? Well, it's really a particularly sort of a very simple fix. You take a volume, you call that a reference. It might be the first, the last, the middle, the average of all your volumes. Different software do it differently. And then you take every other volume, you subtract them, you get a difference image, you square that, you get a variance image. And what you want to do is you want to move the second image so that you minimize the white in that picture, or you minimize the variance, right? And you keep moving, and you can translate it, you can rotate it, and you keep doing that until you reach a minimum of the white or the variance, right? So that's sort of the idea. What happens then is that you end up with a number of matrices that specify, if I take my ith, or let's say second volume, how do I have to adjust it so that I've minimized the mismatch between that and the reference? Right? This is simply how motion correction works. It's a least squares approach for those of you who are familiar with that term. Now, the important point is that you should always look at how much displacement happened. So for example, if you're an FSL user, you're probably familiar with these plots. Other software generate their own kind of plots that sort of convey the same information, but you should always look at them, right? For example, FSL just breaks down the translations from the rotations. Yeah? It also is nice enough to give you kind of a cumulative graph that just tells you how much displacement occurred. And what you really want to do here is look at the scale. Right? Typically, sort of the scale is one of the most important aspects. Right? And of course, if you see big jumps, right, you want to get worried about it. So this sort of at least gives you some kind of quantitative, and then you can calculate the average displacement, the frame displacement, things like that. And you can discard subjects based on this. You can say, we kept only subjects that had an average displacement of X. Right? Of course, no movement is good, any movement is bad. That's just it. But sort of people seem to abide by certain rules. A few millimeters Nobody gets too offended if you keep the data. Not to mean that there isn't motion in that data, but people don't get offended when you write, oh, we've kept anyone that had less than an average of 3 millimeters movement. Jump every now and then. Right? And that's telling you something very important. That motion correction does do some things, but it still leaves plenty stuff in there. There's plenty stuff that remains in model. I'll get back to this point in a moment. But. So what can you do about motion? Well, for one, you can try to prevent it, which would be great. But again, I don't know if you've been into any of these. I've put a friend of mine into this one, and gosh, he hated it. I do not know, how this one feels. People actually now have businesses that will create, will do a 3D image of your head and then create a perfect thing that fits just perfectly in your head. So that then if your nose itches, you can go like this to sort of scratch it against it. I don't know. My personal experience is that anything more than this tends to sort of be hurtful, but according to what experiment you're doing and how precise and things like that, you might want to have more sophisticated methods of preventing it. Right? If you're doing very careful retinotopy, for example, you have very different demands than somebody who is considering larger segments of the brain of activation. And not that both shouldn't have the same standard, but this is more of a traditional approach. Now, once you try to prevent it, then you got to cope with it once it happens. Right? So let's just imagine that that's a time course of a voxel, and this was our task, maybe a standard on-off task. Number of ways you can do this. For one, you can just create a single regressor that pinpoints 1 or 2 volumes that had big jumps. Right? If you're an FSL user, and you should use this even if you're not, there's a little tool called FSL Motion Outliers. It's one line, FSL Motion Outliers, image. Then you can specify some more stuff if you want, but that easy. This will actually create for you a regressor for each jump, each intensity jump that it deems to be an outlier with respect to the average signal and the variance of the signal over time. Right? It's very easy it will automatically create a matrix with 0, 0, 0, 0, 1, 0, 0, 0, 0. And it will have one column per each such detected outlier. You can do this on the basis of frame displacements, root mean square, dvars, whichever is your favorite variable. You can change the thresholds for outlier detection, all sorts of things. But if you're lazy, just type FSL outliers image, and it'll create for you a matrix with a lot of zeros, and for each column, 1, 1. And the idea behind this is that you're trying to suck all the variance of the time point into this regressor so that it doesn't leak into your task, for example. And this is definitely a better option than splicing, which you should not do. You should not sort of cut out, excise a TR, because that messes with the timing of things, the autocorrelation within the data, et cetera, which is very important. Okay. Now, so this would be a very simple way with 1 or more regressors. The standard thing that most people do is this: you take the motion that happened in each of, typically if you're doing a rigid body, each of 6 directions, right? 3 translations, 3 rotations, and you actually use those as additional regressors. Right? And the hope is that any change in variance that associates with the motion in any of these along any of these axes will get caught into the motion regressors and not into your task regressor. Now, in task-based analysis, most people obviously use this. I tend to see, but this is sort of my my experience on it, I tend to see a minimum of 6 motion regressors. Now, most people, particularly if they're FSL users, for example, where there's an automated way of adding more, will use 18 expanded motion regressors. I know AFNI has its own way of producing these too, and I'm sure SPM has something that allows you to do the same. And these additional 18 tend to be the first derivative of the motion, the second derivative of the motion, the difference between first, second derivative of the motion. The idea is that when you have a motion occur, it doesn't only affect that time point. It actually affects following time points too, in a certain way. I'll get back to this in a moment. In task-based designs, I typically do not see much sort of single time point modeling. right, the way I was mentioning earlier. Now, on the other hand, if you look at task-free analysis, then most people tend to use somewhere between 6 and 24 motion regressors. Whether these additional 18 regressors truly do something to mitigate motion is unclear. There is some data to show that they don't quite do as much as we'd like. I see fairly often sort of single time point modeling, as I mentioned a moment ago, sometimes referred to, some people do scrubbing, and I'm not going to belabor on this because you're going to hear more about this further down. Some people also use global signal regression as a means to mitigate things that happen when you then look at correlations between time series. Of course, you know that if you use global signal regression, you're essentially mean centering everything, which also means that if you then care to look at areas and say whether something was positively or negatively correlated, it's difficult to interpret those negative correlations. Now, here's a real life example. In fact, this is one of my patients, not a good one. So these regressors down here, I think it was 4 regressors are my task. In fact, these were seeds. So time series associated with some part of the brain. Expanded motion regressors, 24. And these up here were all the outliers that FSL judged were outliers. Right? So this was actually my X matrix. And of course, if you think in stats terms, you look at this and you think, well, gee, you're losing a lot of degrees of freedom, right? Which I sure am. Of course, usually we don't test statistically at this level, so people don't get as upset about losing degrees of freedom at this first level. Our statistical analysis tends to be at the group level, so the degrees of freedom at the first level are sort of less problematic. If you analyze this, it has a profound impact. In fact, you notice that on the left, where they didn't use the spike, they didn't look at the outliers, you really lose a lot of the key areas that people consider being part of certain so-called resting state networks, whereas you do recover them if you include the outliers. Right? So this has the potential for being pretty important. One additional way of doing this that I think is particularly cool is to actually use what is called a prospective motion correction. And the idea is very simple and great, which is, so just assume this is your volume, and the yellow box around it is your acquisition box, right? So let's say there's an acquisition box around my head. If I move, right now I'm moving within the acquisition box, but the acquisition box traditionally doesn't move with my head, right? So that's how you lose the correspondence between voxels and part anatomical locations, etc. So the idea behind prospective motion correction is that in between TRs, you take a really quick, I think less than 80 milliseconds image. And if you notice that there's a delta, there's a big change in the position of the intensities, you infer that there has been motion. And so what it does is it automatically rotates the box to try to track that motion. And now, in a sense, you're trying to follow the head, right, as it moves inside the MRI machine. You're trying to adjust the box, the acquisition box, with the head. If you want a very nice example by Ward and colleagues, the top row shows you a certain slice before and after rotation without using the prospective motion correction. Whereas the bottom slice shows you one slice and that same slice after a motion if you have used the prospective motion correction. And you'll notice that while here the anatomical locations have clearly changed inside that slice, that has not happened in the bottom row. So it's a great idea. I've used it with some success in a recent sort of study. I was very happy with it. I think this comes default in many scanners. So if you're concerned with motion, this is something you could use. Although I'm not sure that the downsides of this type of approach have been fully explored. So I'm not sure we know whether it comes at some cost or not. We tried something last year, in fact, in the NITP, and there was some lack of clarity on whether this worked well for task-free type designs. But all right, so motion correction is great, right? It's something you really have to do. However, even after all of this motion correction, plenty of movement artifacts still remain. There's residual uncorrected motion. You've seen this in the example I gave you in the 2 clips side by side. Really, there's no way of detecting rapid movements within a scan. Really, our motion correction assumes that the subject is nice enough to move exactly in those few milliseconds between the end of one volume and the beginning of the next. If somebody were to move like this and go back to reasonably the same point or a similar point during a volume, you would never know that. So plenty uncorrected motion. Now the truth is that, and I was hinting at this before, there are spin history effects. You know at the beginning of each scan why you drop the first 4 TRs? Because it takes a certain time to entrain the protons in their sort of radio frequency, down, back up. It takes time to entrain them into this rhythm. If you now move, a given proton from somewhere in your brain will have entered a different rhythm. And just imagine that the proton hasn't had time to come back to its, to alienate with the field. If you now try to inject a radio frequency pulse and you try to get the proton back down, you won't be as effective in doing it, which means that the signal that is going to be returned will be lower. So now, just because motion happened in 1 TR, you will now get a different signal, potentially lower, in 1 or 2 following TRs. So spin history effects, and there's an asterisk because the prospective motion correction, on the other hand, has the potential for diminishing this issue. Right? And of course, you might imagine that if your field is not just perfect, you could imagine voxels now sort of changing the exact magnitude of the field they're in, which again could be problematic. And of course, as I mentioned earlier, task-correlated motion is sort of one big issue. And this is something you can do something about beforehand, right? Before ever getting there. So what's the moral of the story? Hey, stop people from moving. Again, nailing their ears to the bed is frowned upon, but you can make sure they're comfortable beforehand. This is where setup time is actually very valuable, right? Make sure they're comfortable, make sure you tell them motion is a problem, train them maybe. Some people, particularly if you're working with children, some people often have these mock scanners where children play video games and every time their head moves, the video game freezes and they sort of train themselves to stay still. I don't know if you can legally, by the IRB, reward someone for not moving, but you could say, your payment is sort of contingent upon how much motion you did. I don't know. But you get the gist of what I'm trying to say. And of course, the really important part is that you want to decouple motion-prone tasks from cognitive events of interest, right? If you can, try to insert a spacing between whatever is the cognitive thing you're interested in and the actual motor response, for one example. And of course, you want to model motion out. And if needed, just reject a subject or around. And if your experiment is about the vanilla, 20-something-year-old undergrad, look, there are plenty of those where you come from, right? You can always find one more. Of course, if you're working with very, very precious populations, you flew someone in from Alaska because they had a certain genetic, mutation, then sort of, it's harder to reject someone for motion. You might try something else, but you might try to sort of bend over and backwards to try to fix it. Alrighty, so this was really sort of the main offender. Let me still go over some important points, but I think some of these you're very familiar with. Spatial filtering, known as smoothing, blurring, right? You all do this. And the idea is really that you're going to replace each individual voxel with a weighted average of that voxel and its buddies around it. Yeah? If you're not familiar with the term, I just like breaking down the full width half max, which just means that's how you communicate to other people how much you're smoothing. When you tell me that your full width half max was 5 millimeters, what you're telling me is that the width of the Gaussian that you used to smooth at half of its maximum was 5 millimeters. Right? So in my mind, I can picture a Gaussian of a certain width. Right? Now, this has advantages and disadvantages. Obviously, it increases signal to noise. Right? Because you're sort of wiping up, you're trying to clean up some of the random noise that is happening. If 2 voxels are nearby, they're probably doing something not too dissimilar. And just by averaging them in some way, you might kind of get rid of some of that random noise, which is great. And what applies here is the matched filter theorem. Right? The maximum increase that you get is if you apply a filter that is exactly of the shape and size as the signal that you care to look at. Now, what is the size and shape of the signal you care to look at? Well, that's why you're doing an experiment. So it's kind of tough, right, beforehand. So people go with rule of thumb, 5 millimeters, 4 millimeters. There isn't really a good way. People have not done this in any intelligent mode, meaning nobody has really looked back at previous studies to say, oh, okay, these are the type of activations we get, so we're gonna adapt our filter to the type of activations we expect. However, this does mean that you're either under or over smoothing every time you do this. Right? In fact, some parts of the brain you might be under smoothing, some parts of the brain you might be over smoothing. Right? which means you're helping some parts of the brain, you're hurting some other parts of the brain. An important reason for doing this is that it allows you to use Gaussian random field theory. We're going to talk about this later. It's one of the ways in which you correct for multiple comparisons and sort of ponder over issues of significance. And of course, by slightly smoothing, it might also alleviate the problems of matching individuals that might have different anatomy or different functional neuroanatomy. Right? Now, of course, you're reducing spatial resolution. I mean, you spent all this money to get something that gives you these really tiny voxels, and now you smooth over them. That's just terrible. And if you over or under smooth, right, you're hurting what you're looking at. If you over smooth, what happens? Very obviously. Sorry, if you under smooth, what happens? Come on, if you under smooth. If you have something that's bigger than your actual size of your smoothing, what happens? Hey, exactly. You're not getting your bang for your buck, right? You could get much bigger bang by smoothing the right size. If you over smooth, what happens? Exactly. You're bringing in activation increases, but you're bringing in junk that is not signaling into your signal, which means you're hurting your signal, right? Obviously. And if you want to get a visual for sort of what happens as you smooth more and more, this is a beautiful animation from the FSL people. You can see that 0, 5, 10 millimeters, 20, right, full width, half max. There is an area between 5 and 10 where you are boosting your signal, but after that, you see that you lose activations, right, as you over smooth. And that's exactly for the reason I just mentioned a moment ago. But you know, this is sort of not too controversial. The one that is particularly important, particularly for those, particularly sort of in view of task-free analysis, is temporal filtering or temporal smoothing. Now, both task-based and task-free analysis, you can think of it this way. You're interested in oscillations that have a certain, frequency. Right? If it's a task, you're interested in stuff that goes up and down and wiggles at the frequency of whatever your task is. If you're interested in, if you're doing your standard the resting state kind of analysis, typically people seem to be particularly interested in the low end, right, of the fluctuations of neural events. So in both cases, you are doing this kind of smoothing. Now, you're interested in a specific window within the frequencies that you get, but of course, there's a lot of other stuff that creeps in there. And I mentioned, a lot of these earlier. I should say, currently in fMRI, most of the noise has this 1 over f, so you get a lot of noise at the lower frequencies. Equipment-related noise, now this can come at any frequency, right? It could come at any frequency, but I would say most of the times I see this, we're at the very low frequencies. Now, the physiological ones are complicated. You get cardiac respiration, maybe between 40 and 120 beats per minute, or 12 to 20 breaths per minute, which gives you certain ranges, but they always end up aliasing into the low frequency because we're sampling slower. And so we tend to end up seeing, we're sampling these events slower than they are, so we end up seeing these slow fluctuations. So even sort of higher signals end up at the lower end of your frequencies. And of course here, as our TRs get faster and faster, it might be easier and easier to use these type of filtering to get rid of, for example, physiological noise. Motion, as I showed earlier, all over the place, but we have ways for coping for that. So here's a visual for it, right? Imagine you have a task. Green is what you're interested in, right? Your task might be happening exactly every 30 seconds. I have a period of 30 seconds. And then maybe it has some harmonic higher up. But the noise, what you're interested in is whatever happens somewhere around here or somewhere around here. But the noise, of course, right? You get noise all over the place. Particularly, you get noise up here, right? So the noise that I circle here in white, that's kind of easy, right? This is almost evenly distributed over all these frequencies. So it's easy to cope with just by averaging. What is difficult to cope with is structured noise, because this, you don't get rid of it just by averaging. So we got to do something about it, and that something is temporal filtering. Just by the way, if you just look at this, you can already tell that this example makes clear that the signal-to-noise ratio, right, is terrible, certainly smaller than 1, right? The noise is dwarfing in terms of its power your signal. Here's an example. This is our time series that I showed you earlier. And let's just say that let's add in there, right, a linear drift, which might happen. And now your signal is this. Or maybe you might want to insert in there, you know, a sort of a U-shaped drift, right, low drift. And now your signal might look like this. Or maybe you might have in there excessive high frequencies. And now your signal looks much more wiggly than before, right? So what we want to do is we want to get rid of all these things that are not pertinent to our task and that we might explain in terms of motion, drifts, things like that. Right? So the idea is to use, for example, a high-pass filter. The idea behind a high-pass filter is pretty simple. You literally say, you take your time course, you look at the power spectrum, and you say, can I just ditch anything that is irrelevant to my task, i.e., anything that is slower than a certain number is probably unlikely to be due from my task. It's more likely to be due to all these other sources. Can I just get rid of it? That's exactly what a high-pass filter does. Right? This is the shape of a high-pass filter. So take that last box on the right. Imagine that being a knife and cut off in the middle graph anything that falls outside, right, that area. So essentially what you're doing now, you're cutting off all this crap up here. Notice again that your signal to noise ratio is terrible. Right? Now apply a high-pass filter, and now this is what your time series looks like. Right? And again, you've lost sort of this big drift. Right? And indeed, if you take the power spectrum of your new time series, there you go. Now your signal is actually the power peak. So now your signal to noise is much better in terms of the power at that frequency. If you want a sort of a real-life example of a event-related design, it looks very different. This is a jittered event-related design. It's less easy to tell where my task is. Right? In a nice block design, you know exactly the frequency of your task. Right? It's a periodicity of your on-off sort of blocks. In a jittered event-related, it's much more difficult, right, to find what is that number. There is software that will help you find out what it is, but the idea is the same. So here's the time course. This is a power spectrum, apply a high-pass filter, and as you see, you're kind of getting rid of this initial, right, big spike there, which you know is unlikely to be due to your design. The low-pass filter is exactly the same thing, but the other way around. Right? You get rid of stuff that is too high to be of interest to you. For example, if you have this artificial sort of high-frequency fluctuation that I've put into the signal here, you look at the power spectrum, there's your task right here, and this stuff here is crap that I injected in there artificially, just to make this look really squiggly. Yeah? So the low-pass filter, it has a slight different shape in terms of its rollout is less steep than the high-pass filter, but the idea is the same, right? Imagine this as a knife that sort of gives a number of 1 to anything here, and then lower and lower numbers until it's really nearby 0. Essentially, you can put it here, and you're kind of cutting off, right, anything that is too high by whatever you set the low-pass filter. So now you do that, and there you go. We're back to our original, right, nice time series. And if you look at the power spectrum, yet again, right, we get this, we have the peak of our task, but we lost sort of that high frequency that was not relevant to our task. And of course, I can do this because I know that that cannot be due to my task. And so I try to explain it, say, well, that's probably noise from the equipment, so let me just cut it off. Right? Let me just excise it. Okay. I'll just skip over this thing. This is just how this gets implemented. And I'll just say that there are two different ways of doing it. One is the SPM way, which essentially is just saying we will add low frequencies inside the design matrix, and you know those low frequencies will get captured by these regressors. And you can see here an example of the type of regressors that get added to your X matrix. FSL has a different philosophy usually than SPM. They like doing data-driven stuff. So they actually go in and say, in the data, and say, let me see what low frequencies are in here. And by using a Gaussian weighted running line, you essentially end up seeing that this line right here, the pink line, is the low frequency, and then you remove that. Right? And to give you an example, you start from the red line, and after you've removed the low frequency, you get the green line. And you can see, for example, that the time series here got dragged a little bit down, right? And let's see, yeah, and here it got dragged a little bit up. So this is the type of adjustments that you can do. So only because a lot of people, yeah, great. I will finish with one thing about brain extraction. I've left these slides that I won't really cover in the handout. But let me point this out. If you're not doing, if you're not doing analysis on your standard, very nicely shaped brain, brain extraction can be problematic. The idea behind brain extraction is to separate what is brain tissue versus non-brain tissue, right? And this is often used for a lot of, sort of underlies a lot of analysis. Fairly typical to do this in certain software packages for functional data too, but if you're doing structural data, for example, this is very important. Now this becomes very difficult if you get brains such as those that I typically look at. And these are 3 different patients, and you can notice that the shapes are not quite your standard average undergrad. I mean, some might, but, or you might have, one particular problem that we often get is sort of big enlargement of ventricles, and so that throws off a lot of the tools. If you were just to take, for example, these 3 brains and put them into the conventional tools that you get, this is the result. In gray, you're seeing the result of the tool. In green, you're seeing a manually sort of a manual brain extraction. So the perfect brain would be the one that matches, the perfect extraction would be the one that matches perfectly the green grid. Yeah? You know, not quite what you want. I mean, this one here, for example, I took off the name because it's sort of, I didn't want to do bad advertisement. But here you have all the neck, which you don't really need, or here you might have all this excess out here, right, which you don't really need, or all this growth out here, which is clearly non-brain. However, if you sort of, with some engineering, you can end up doing a pretty good job automated. So one way is that you actually do these manually, but it's very time intensive. So if you're using, if you see populations that sort of are difficult to work with, there's this software which you can download for free. There's a link down here, and there's a paper that's going to tell you all about it. But you can get some pretty good brain extractions in an automated way. So if you don't have the time to actually do it manually, to correct it, there is some extraction. The reason it works so well is the following. Here's how it actually works. By the way, OptiBet is the name. And you can find it somewhere on the FSL website too. Imagine you start with this brain, and you can notice this is the head that has sort of this, all right, this big deformation here. What we do is the following. We do an initial brain extraction, an approximate one of those that is crummy. See all this stuff out here that is not brain, that is still in there. Then we register it with a linear and nonlinear to the MNI template. We register the bad brain extraction. And then we take an MNI mask, one of those that FSL gives you or that you can find anywhere online. And we bring that and we apply the inverse to it. So now we take the nice mask and we bring it back into the space of the head. And then we simply punch out, right? We do a punch out from the original head image with the inverted mask. And then you actually get a pretty good, right? You can see here that now we've lost all the stuff that was hanging out on the sides. So if you don't have the time to manually adjust it, this is a very neat little tool that you can use. If you have FSL installed on whatever cluster you use, just download that script and type one line, optibet.sh image. And that's it. And if you want to read all about it, there's a paper, and the script itself will give you all sorts of instructions. And yeah, I'm going to leave it to this. So I'll gladly take questions, or maybe I'll take lunch. Well, what am I taking? I'll take some questions if people have them. But I'm around for sort of most of this too, so if you feel shy, you can ask me later.
We've left an hour and a half break in here. We tried for lunch. There's plenty of time for that. And we're really encouraging questions.
Yep, take the mic.
Is it working? So I have going a bit out on a limb here with this question about task-relevant stochastic noise. So the idea that the internal white noise in the system, if it matches the frequency of the task, it could push below threshold processes up to perform the task. And so do you know if there's a way that that can be modeled separately from the task-based signal and also from the noise that you're discarding?
So if it's white noise, by definition, it shouldn't, right? White noise, by definition, should be fairly even across all frequencies. But I understand what you're saying. What if you do have other things? Once it's close to your task, I could imagine using things such as added regressors, for example. If you measured cardiac, if you actually measured with a pulse oximeter or sort of, the breathing, then you could use that to try to get rid of structured noise of that sort. If it matches your task, it becomes very difficult because anything you get out of there could either be your task or it could be, I don't know how you would tell apart which part of it is task and which part of it is non-task, unless you have, for example, additional regressors. Even if you used an ICA and just say, yeah, show me everything that is there, unless you've already trained, here, I could see this happening. You've previously trained a classifier using one of the available tools, which I think we're going to discuss later on, to recognize what is noise and what is not noise in your typical, in your scanners, in your scanner. And then it might label some part of that as noise, but I don't know how it would tell apart which part came from the task and which came from the noise. So once it matches, it's a problem. Actually, you know what? Even if you use the regressor that is the cardiac, once it matches, you're going to end up losing most of your signal into that. So the answer is don't have that kind of noise in there.
Hi. I was wondering how multiband imaging can affect slice timing acquisition.
Yeah. So I'm not the right person to answer that. He is, but this leads me to a slightly different point. Multi-echo images will have a great, I meant to add a slide about this, but then I was sort of going like this and trying to get a baby to sleep. Now, multi-echo is extremely interesting because imagine you do this. If you take, and there are a couple papers out already, and there's one that is going to be out shortly. Imagine you take 3 different echoes at 3 different, shortly, who knows, 15, 25, 40, something like that, milliseconds from the initial injection of the radio frequency pulse. Now, everything that is a typo, everything that is a real T2 star should have a certain decay. Right? You know exactly what is the decay that things that are induced by the radio frequency pulse and the proton coming back up and pulling out a signal, essentially the Bold effect. You know exactly how that should work. So you can look over these three echoes, and if things don't have a certain shape, then you can say that's probably noise. Right? If something doesn't, for example, sort of come down nicely, just to put it in non-mathematical terms, then it probably is not biological in origin, but it's an artifact. For example, if something had intensity that wouldn't change over the three echoes, then it's probably noise. Right? It's probably non-biological, i.e. noise. So that's a nice way. That's something that I really hope. I mean, that seems exciting to me. And Professor Cohen is going to tell you everything about how the multiband is going to help that.
It's a 2-part answer. The first part sort of initial, we will have a talk on multiband next week. But essentially the idea with multiband sequence is you excite 2 or more slices at the same time. And so if you do, say, a 12-slice acquisition and multiband 4, then you're actually doing 3 sets of 4 slices. Those 3 sets of 4 slices are going to be offset in time, interleaved the way the other ones are here. So you could calculate at what time every single one of these was acquired. But as far as slice timing correction goes, the default slice timing correction is actually agnostic to how the images were actually acquired. It doesn't know the slice timing, so it just interpolates across the time points. And as far as that goes, there'd be no difference in the errors from multiband versus any other sequence.
I'll just add that in my read of the multiband literature with respect to slice
I can tell how much you want it.
So most multiband studies tend to use very short TRs. That's the point of going multiband, that you can acquire whole brain data in less than 2 seconds, and often on the order of 1 second or less. So most studies, including everything that the Human Connectome Project has been doing, do not do any slice time correction, because when your slices, if you're acquiring, let's say, 4 slices simultaneously or 8 slices simultaneously, and they're only separated by, I don't know, 200 to 500 milliseconds apart, the slice timing correction is not going to help much, but it could hurt by moving noise characteristics around or smearing across slices.
So speaking of the slice time correction, so I'm wondering, so one time instead of correcting it, try to do it, just leave it alone and adjust it during the modeling part. Then
Yeah, that would be sort of, you know, you would create a slice sensitive model that would be different in its timing for each slice.
Right.
It's just people haven't done it, but absolutely.
So I have a question about adding motion regressors, like individual time points. If you're-
Like individual spikes.
Yeah. So if you are changing degree of freedoms on subject level,
Yep.
How do you really then compare to groups where one group has clearly more versus less? Or how do you pretty much solve it at a group level, in a way?
Yeah, so the answer, the empirical answer is no different. Right? People do not usually get in your vanilla experiment, people do not get concerned with degrees of freedom because you're usually not doing any statistical, you're only estimating at the first level, you're not doing any inference on those maps usually. Unless you're doing a single subject, maybe you're doing a patient report. And then let's say you had 2 patients and you were just sort of doing kind of a comparison. If one of the 2 patients had a lot more, many more spikes than the other one, A, you would know that the 2 patients differ in motion, first of all. But B, if you're then doing significance maps, then yes, one of the two you had fewer degrees of freedom to play with than the other, in which case it would certainly be a problem. People usually don't get concerned with it, A, because you have so many degrees of freedom. You usually have number of volumes -1 to begin with, and you know, at the current sort of at a 2TR, that's about 300 volumes. So even if some 30 of those, you know, go into my regressor as well, so be it. But second, as I said, people don't typically do any inference at that level. So the only degrees of freedom that are relevant when you're doing your vanilla experiment are n, big N. I mean, small n is also relevant, and also tomorrow we're going to get into the details of how small n also plays an important part. But people usually are just not concerned with it in that way, you know, at the first level.
I was just kind of wondering why correction for physiological noise and sources isn't considered part of the standard preprocessing, especially given kind of you can have secondary effects with change in heart rate, change in respiration, things like that.
Yeah, you're right. I mean, it's so easy to acquire. You just put a little pulse ox here on a foot and then write a little strap here to capture. So all I can tell you is my introspection on it. Having seen some data where it made very little difference, I've never seen it make a huge difference. Not to say that it couldn't in some cases, but when it has been acquired, for example, when I've acquired it when it was elsewhere, I've never seen much of a difference made. Now the question is, if you did see much of a difference, then is that data good to begin with? Right, so then you get into these kind of hairy decisions. I just don't see people use it often, and when they have used it, I just haven't seen that much. It should make a big difference, but I just haven't seen it. I'm sure it could, but yeah.
Yeah, logical noise.
Yep.
So I assume, you know, inside the brain there's a time delay, different part, you know, according to how far from the blood vessels or this. So how
Where in the brain also?
yeah, So then how to take these things into account?
Look, you think that you could model a lot of it, but I absolutely agree. In fact, that could be the reason why it doesn't make as much of a difference, because it's a bit of a cruder measure with respect to the complexities of how this translates, or maybe how the heartbeat rather translates. Yeah, yeah, good point.
I was wondering how the motion correction procedures that you talked about might do better or worse with spikes in the motion versus like a low frequency kind of drift.
I'm sorry. Versus
Like someone moving slowly throughout the scan away from where they were initially. Oh, you mean if you have like a spiky versus a slow? Exactly.
I'm sorry. Yeah, right. Somebody sort of like going versus somebody slowly creeping. So if you've ever used those NASA pillows that at my first institution we loved and we thought those were the best for subjects, you get a slow sink, right? Do you know the foamy pillows where it's slowly? So since we thought of that, they've discouraged the use of them. Here, the big jerks will produce big problems, and in particular, they will keep giving you very big spin history effects. The slow drift is also going to give you that, but because it's slow, sort of at each tiny sub-millimeter of motion, it's going to be less problematic. I don't think that you should be any less concerned if you had if I had a gun to my head and were asked to choose, I'd definitely get the slow drift between the two. But of course, they're both bad. Now, don't put the gun to my head. I'll pick one, regardless.
I had sort of a related question, just thinking about integrating the different motion correction strategies that you talked about, and if we're applying this sort of spike regressors and controlling for motion, and can you salvage subjects that maybe show a large degree of motion, or where, how do you make the determination that this is just so much that they have to be thrown out, and does that differ between task-based versus task-free analysis?
So, no motion, keep. Yes motion, bad. Now, how bad is bad? I can tell you that if you read the literature, most people will say, well, anything that has an average displacement of less than 3 millimeters, I'm going to keep. Now, if you're doing a block design where you're hammering visual cortex with a flickering checkerboard, sure, motion will do something, but you're less concerned that if you're having maybe either a quick event-related design or a task-free design. If you have a task-free design, if you keep it slightly backwards, it won't point to that, and it will not get feedback. The task-free design and the ensuing analysis that people typically do after that have been shown to be so damn sensitive to motion that you probably want to be more careful. Not to say that you shouldn't be just as careful in a task-based design, but the effects of it are so disruptive. I mean, your result will change completely. In a task-based, there will be differences. I don't know if it will wipe it out in the same way. In fact, I don't think. I haven't seen it wipe it out in the same way. One thing that you can do, you can just chop. Imagine you have 300 volumes acquired, and there was a big jump at volume 282. Then you can just chop it off and sort of call it, the first 281 your data. Of course, then that is going to introduce some difference, because maybe if you're doing a correlational type analysis, the correlations will be different. But overall, you do know that correlations, after about 5 minutes of data, your correlations tend to be vaguely stable, at least at the level of big default, big networks. Whether that is the same true also in graph theory type analysis, not sure. So it's all of this is a judgment call, except your reviewer will have something to say about it for sure.
Let's do only one more, and leave enough time for lunch and getting to the next talk.
Hi. I have seen the intensity normalization in the order, but
yes.
I think you do not mention that. I have one question for that. That is, when you do the intensity normalization, can you take account of the intensity difference between the cortical region and the subcortical region?
So there are two types of intensity normalization, and I'm not sure which of the two you're thinking of. One is what people do, which is also referred to as grand mean scaling. You take the whole time series and you force the average of the whole time series to be at a certain number. For example, if a cell forces the average across the whole brain or whole time series to be at, I think, 100 square. The other one...
And that is all the voxels?
Yes, the average of everything, the
Okay,
full
okay.
time series across all voxels, yes. It does not take into account cortex versus non-cortex versus subcortical versus intensities at white matter. If you're thinking instead of the intensity normalization where you force every single volume to have the same average across the whole head, then that is a no-no. That sort of is vestigial from PET, where the intensity of the tracer was decaying over time, so people would adjust for it that way. But for example, if a cell used to have this second type of intensity normalization, they since removed from the GUI the button to do it. And you shouldn't do it. There are quite a few published papers showing that it gives big differences, and it's not a good way of fixing any artifact. Yeah. Okay, great. Lunch it is.